I will start here with the introduction. My name is Roland Larsson. I'm a professor of machine elements here at Luleå University of Technology in Sweden. The slideshow I will show you now is not at all an attempt general on this. There are many ways to model and simulate component systems, but this is one way you can do it, and one important way to do it, I think, and fundamental way to do it. I can hope that you will learn pretty much from it. The outline is something like this. We'll start asking ourselves what is a model and what types of model exist, and do we need to follow any laws, and how do we do the modeling. I will briefly talk about something called efforts and flows. I will focus very much on lumped mass models, and I will try to show you the similarities between mechanical and hydraulic and electrical systems, and I will show you a few examples, at least one example with Simulink, how to solve the equations with Simulink. First, we can discuss what's a model, and that's pretty straightforward. The model is something else than the object or system or even ID than itself. So it's a representation of an object, a system, or an ID in some form other than itself. And you use a model because a model can be used, should be easier to use, should be have a lower cost to use, be faster. You should be more practical, and it should enable you to study different design alternatives. So the models we are talking about here are physical models of mechanical systems. That means that we more or less make a computer program where we simulate the behavior of the mechanical system we study. So instead of making the mechanical system, we actually model it and simulate it in the computer, and for that reason we can of course make it much faster and much cheaper, and study plenty of design alternatives before we are starting to manufacture the actual system and do experiments. Maybe that was something obvious, so let's move on to the laws we need to follow, because I will show the process to set up the set of equations you need for the model, and all these equations are based on some physical law. For example, in mechanical engineering, force equilibrium must be there always. Also flow continuity and mass continuity. That means that what comes in should also go out if it's a stationary system. Material continuity is what I mean by that is that if you put two components cannot add into each other, can't penetrate into each other and add the double mass. That's a kind of a boundary condition also. Energy conservation, of course, can't destroy energy, as you know. Heat and power balances, that's the same as with flows. Heats and powers must balance each other over a kind of system boundaries. We also assume that, that's a law, that there is a continuity of speed and position of something. So if you imagine a component, for example, this component can't suddenly just jump to another speed without, it must take some time, and it can't jump to another position without spending time in between. So that were the laws, and then we're coming to a systematic approach to mathematical modeling of the systems. And here I'm just showing the perhaps straightforward way to think when you set up a model of a system. But I think it's a pretty useful cookbook, and we will practice that now. I will show you in reality what it means to make it easier to understand. So the first thing you do is to define the task. What is it we really want to know? What do we want to know? How the function of the system, or is it the strength of the system, or is it the energy consumption of the system? That depends, varies from problem to problem. Next step is to define the nature of the system. You need to identify the variables that characterize the state of the system, and you may also identify subsystems. That means that you split it into smaller parts which are easier to grasp and handle. And here you also think about what is important, what's not important, what is dominating in this problem. Then you create a model. That means that you identify the equations, you set up the equations in some way. Normally it could be force equilibrium, flow continuity, as I will show you. But also other equations are necessary in this case. Then after a while you will see here, oh, it's pretty complex. Then you need to simplify a little bit. And after that simplification stage, it's time to solve the equations. Now when you have the set of simple enough equations, you can start solving them in some way. And when you have solved the equations, you try to verify the result. Is this the right result? Did I solve the equations in a correct way? Is it the correct answer? So that's very important that you really solve the equation correctly. Otherwise, you may say that this model is crap before you have seen that it's pretty okay. So and the final step is of course to validate with experiments. So if you have you have solved your equations, you have a result, but is the result okay? Is the model good enough? That's what we want to know by making maybe a few experiments, or experiments and parts, covering parts of the model in some way. So that's do we solve the correct equations? Do we have the right model? So these two steps are of course very important. Do we solve the equations in a correct way? And when we have solved the equations in a correct way, did we choose the right equations? Okay. So the success in this relies very much on how well, for example, how well the system was isolated from the environment. I mean, a system is connected to the environment and it goes on forever. You need to model the whole world in the end. But normally you are able to isolate only parts of this system, and if you find the correct boundaries, you can make the model much simpler, and you don't get any effects from the environment. That is also if you split it into subsystems. So if you make it to small systems, a number of smaller systems, then that's also a success factor, because it's easier to handle each small subsystem. But if this subsystem is connected to other subsystem in a way that you don't take into account, you may run into problems. We also need to have not too simple models, but not too complex model either. And of course we should choose the correct equations, and we should choose the correct interface equations. That is maybe something new for many of you, but in this case we see it as very important to, if we model a system like this is a model machine system, we really need to model the interfaces in a good way. Interfaces here between the gears, in the bearings, in a coupling here, they are very important in order to model, for example, the dynamics of this system. The dynamics will strongly depend on the interfaces here, the function as well. So it's that's also very important. So this is a graph showing the modeling and simulation process kind of overview. So the first thing you do is a kind of project description. You know what you want to know. You make your conceptual model. I mean, trying to understand what it is you want to learn. You make your simulation model. That's you're defining the equations, and then you program these equations into some kind of simulation program. And then you check, do you trust this model? Is it good enough? If it's good enough, then you go on to the simulation phase. But if it's not good enough, you go back and improve the model. So this is the verification and validation phase. You may also do experiments to validate the results if you are able to do that, or if you have the money to do that. But when you have your model and you are satisfied with that, you rely on that, then you go on to the simulation phase and you vary the different parameters in the way you want to do. You check what you solve the equations in the way you want to. Although you solve the different cases, study the different cases you want to study, and finally you draw some conclusions from that. That's an overview of how simulation normally works, especially in mechanical engineering. So an example: you have a wheel suspension of a car here. It looks pretty complex, doesn't it? And you have some load here coming from the wheel road contact. You have some springs, you have some dampers, and the first question is, what's the task? Well, in this case, you may say like this: you want to know if I suddenly apply a force like a step, you drive over pavement or something with an amplitude A, how will this wheel move directly after this step is applied? This is kind of shock load to the wheel system. And next question is, what's the nature of the system? And what are the variables that characterize the state of the system? Well, then I made the following simplification, sorry. In this case, as I said, it looks pretty complex, but in reality it's a spring and it's a damper, and there are some metal around it. It's the wheel and has some weight, some mass. So the first simple model of this system could be a mass with a spring and a damper, and the damper could be a piston with a hole here, that when you move here the fluid down here, if you move downwards, the fluid must be pressed through the hole to the upper chamber, and that gives you some damping effect. So a model like this is pretty straightforward model, and you can learn, if you can get characteristics of the spring and the damper that are proportional or the same as the system here. And so another example is this hydraulic actuator. First is define the task. What do we want to know? You can actually stop the video here and ask yourself, what can be interesting to know here, understand or estimate? You have a cylinder here, you have a piston, you have some mass connected to this piston, and at the moment it is moving at a speed v to the left. What could be interesting to know, to learn? Well, one task could be to answer what will happen when the piston enters the left cylinder wall. Is there any risk that the piston will damage the wall? That could be one task. So when this piston just moves with the speed v, it comes in here and it is approaching the end here. So it will it just crash into that left end of the cylinder wall? Well, before answering that question, we can discuss the nature of the system. What are important variables here, and can we draw some conclusions or make some assumptions about the system? Do we need to identify subsystems? Well, I would say that this is a rigid system, and because fluid is a fluid, and you should also take flow balance into account here. So the fluid that comes in here and presses the piston to the left must also come out here. The same amount must come out here. And when this part of the piston is coming in here in the more narrow part here, something is changing. That is an interesting thing, isn't it? So this part of the system needs some attention, I guess. And the pressure here in this chamber is important, and the pressure out here is important, because if this pressure increases, then this piston will slow down. It will damp this motion in some way. So, and why will this pressure increase? Well, if this smaller part of the piston is coming into this part of the cylinder, then suddenly there is a flow constriction here, and there's a problem for the fluid to escape, and then the pressure will increase, I guess. So again, the flow through this part is interesting. Okay, so then let's move on to the next step, identify the equations. Well, that's the laws. Which are the laws we need to follow? And as we need to introduce assumptions also, I made already assumption that it's rigid wall here and that we have flow balance and etc. You can stop the video here and think about this a little bit before you watch the solution. Okay, equations then. Well, as we said, the laws, force equilibrium, we must think about that. So the force equilibrium, that means Newton's second law. That means that the mx dot dot must be equal, the inertia forces must be equal to the forces applied in the other end of the piston, and that's the pressure multiplied by the area here in the outlet side of the piston, and the pressure multiplied by the area on the inlet side of the piston. That means that it's P in multiplied by A in minus B out multiplied by A out. We also need to consider flow continuity, and then what's the flow in? Well, the flow in must be, the flow out must be this area of the piston multiplied by the speed of the piston. That's the x dot. You remember that x dot is dx dt, so it's the speed of the piston. So the area multiplied by the speed, that's the flow. That's a flow coming out here through the outlet, and the flow into that into the chamber then is you can get that from thin film theory, which is another video you can watch. So actually the flow here through this gap is described by this equation, coming back to how. So okay, the damper chamber, this is the damper chamber. So this is the flow out from the damper chamber, and this is the flow through the channel here. So, and these two flows must be equal, otherwise there will be some flow going somewhere else, into some funny place. Here we now assume that we are laminar flow, we assume that we are concentric shaft here, we assume no increase of temperatures. So let's move on. Coming back to the thin film theory here now then. If you watch the video about lubricant or lubrication, the lubrication theory video, you can learn a little bit about the flow through a thin film. This is a thin film. This is very much thinner than the length. So the flow through the film is just speed profile through the film integrated over the film. That means an expression like this. You can again watch the video, and you end up with an expression that the flow through a film is something like this. So if you assume now that this is a damper chamber, you have the P out pressure out here, and you have some outlet pressure here, which can be assumed to be 0. And in our case, this film is constant, so it's a constant film all the way here. So H is a constant, viscosity is a constant because we assume that the temperature is kept constant. The speeds are not constant. One surface is stationary and the other one is moving with the speed of the piston. So that's x dot actually. And dp dx, that's the pressure gradient. So that's the change of pressure from that end to that end. And that's we can assume that we have a linear decrease of pressure from here to there. That means that we can rewrite this equation to our case, and the H, the film, is the clearance between the piston and the cylinder. The speed, as I said, is the x dot. The pressure gradient is the P out pressure divided by the length of the length of the film here, and that length is varying. The further the piston penetrates into this hole, the longer it will become. So the Q now will be something like this, and putting it into our equations, and also remembering that this was the flow per unit width, and knowing that the circumference of the film is pi multiplied by the diameter of this part of the system, then the Q through the gap here is defined by this one. So we combine all the equations to one equation. Actually, you can get rid of some of the parameters, and you can simplify this by doing this, and then the constant C is just contains constants: viscosity, the clearance, areas, the diameter. So it's that's a constant. So you actually, in this case, you end up with a nice equation like this. And this is actually it's a differential equation, but it's also a non-linear differential equation, because you have x multiplied by the x dot term here. And this equation will be solved in the next part. Thank you.